Hello everybody, welcome to this webinar. Today it's all about bulk solid ingredient measurements and inventory measurements. Before we start our webinar, I would also like to show you how the webinar panel can be used. So of course you should see our webinar presentation in the center. In addition, you can see us via the webcams. Also, you can download the webinar presentation in the download section. We put a handout there that you can use and of course also spread within your organization. Whenever you have a question during the webinar, you can ask these questions in the question fields. So we try to answer as many questions as possible. In case that we cannot answer them, we will follow up afterwards. And also just to let you know, this session will be recorded. So we will put the recording of this session on our webpage on endres.com. I will show at the end where you can find it in case that you would like to watch it again. The presenter of today is my colleague Ola Westgren. He is the Senior Industry Manager for the food and beverage industry in the US. My name is Jürgen Gansmann. I'm the Global Industry Manager for the food and beverage industry at Endres Hauser in Switzerland. And now I would like to hand over to Ola, who is taking over the presentation today. Ola, stage is yours.
All right. Thank you, Jürgen. And thank you for everybody taking the time this morning, afternoon, depending on where in the world you're at, to hopefully learn a little bit more about what the opportunities are to get a better handle of what your inventory levels are in particularly related to solids applications. Clearly inventory measurement is relevant for liquids as well, but for the topic today we're focusing just on the solids aspect. Just some basic things here. Why are we keeping track of our inventory? Real life, there's always going to be a little bit of a time lag between, when things are arriving, when we order things, and when it shows up. So we need to keep some inventory on hand. I know in today's economy, it's a lot about, let's say, just-in-time type of mentality or approach to things. But nevertheless, you do need to keep an eye on what you have on hand and when you need to reorder and so on. And other reasons to keep an eye on the inventories or having inventories is to meet fluctuations in your demand. You may not always know exactly what kind of production is needed for a given day, a given week or so. So demand is going to fluctuate, and for that reason, you also need to have enough product on hand to meet those requirements. As we prepared for this here and over the years, we've looked at a couple of, let's say, trends and observations from the industry, leading you to potentially look at why or what are the challenges in inventory management. First of all, liquids are usually fairly well monitored and kept track on. We found that solids, for whatever reasons, is not necessarily tracked at the same level. But clearly there's a high level of importance to have visibility and full transparency across the organization for what the inventory levels are. It could be for the supply chain side, it's for production and so on. Everybody needs to know what's on hand and when. So that obviously leads, to some of the other points here, making sure you have the correct amount, knowing if you can use it or if you need to sell it or draw it somewhere else. We've also found that in many times the storage capacity is not fully utilized. Many times that's because it's manually monitored, what is inside a silo and so on, and many solids compared to a liquid, solids will settle over time. So you may or may not know exactly how much you have inside of a silo from a level perspective. So often there is a little bit of space on top that is sitting unused. But on the same time, you want to make sure that you're not overfilling and having product coming out from the top of silos, or having to interrupt a load cycle if your silo suddenly fills up. So there's a need to monitor that. And more, because of the just-in-time philosophy, you're also going to have storage at many different geographical locations, regional storage hubs or other locations where things are at. how do you keep track on that, especially if it's a remote location? Maybe you don't have somebody physically be able to go there and have a look at it. And that all then comes together, you know, delivery scheduling and other aspects, all keeping an eye on it. We also have the cost of manual labor and the risk associated with that. Every year, if you go and look at it, there are many people that either get hurt or even die in accidents where they, you know, lightning strikes. It could be falling into silos or falls in general because they're walking on narrow catwalks on top of silos and doing manual checking of levels. So you have the labor cost as well as the risk associated with that. And that then leads to the whole scenario here about how do you stay competitive in an ever-growing environment where the cost of your raw ingredients and the cost of commodities really can come down to, it's like, are you making a profit or not? So we'll look at, let's say, everything from the level sensors. We go quite a bit into the depth of, you know, the selection, what to use where and so on. And then we'll wrap it up towards the end a little bit about the planning tools that are available for you out there to address some of the topics that I mentioned here. So as we move products through a factory or throughout a supply chain, you have raw material coming in, you have some kind of intermediate raw storage. It goes through the different production stages, and then you maybe have a finished product, and then it's getting sold either as a, you know, retail packaged product or potentially in a bulk type of scenario again. And for each step, you need to keep track of what you have on hand, where was it used, and how much is going where. And then that all bubbles up into, let's say, the top level of planning and reordering and so on. So there are multiple different spots where it might be necessary to keep an eye on the inventory levels. For solids in particular, there are many different sizes and shapes and materials of construction used when we're looking at bins and silos. Here's just a couple of examples of what you might run into. You have a large concrete silos. You have smaller steel or stainless steel bins. You have other types of bins, tall, narrow, really large or wide, small hoppers, depending on what the purpose is for there. In all of them, one way or another, you need to figure out, okay, what is the best way to measure either a continuous level or just to have a minimum, maximum alarm so that you know when you're about to run out or when you're going to come towards the top of the silo here. So that's the first criteria we look at. It's like, okay, what kind of silo, what kind of bin it is, and also what kind of control purpose are you looking to use it for. The next step, which also have a really large variability, is what is the product that you have in here. Generally, if you're dealing with liquids, not all that much to be concerned about. But when you're dealing with solids, you have products that are maybe large pellets and grains and so on, like corn or other feed pellets, large sizes. Then you go all the way down to very, very fine powders and flours and stuff like that. So you need to really keep that in mind. You know, it's like, okay, what type of silo or bin do I have it in, and what is the product? So there's two aspects to look at that. And we'll give you a couple of examples here. For sure, we won't be able to cover everything, but kind of give you a guide and a rule of thumb here. It's like, what would be my first step in certain situations here? A couple of the basic criteria that you need to look at as you start your journey down, looking at what the opportunities are or what the options that you have. An area that maybe not always considered for solids is the risk for dust explosion or a fire risk. So when you're selecting equipment to go in there, you need to consider that. What is the risk level of a dust explosion or fire here? And then select the instruments that are then rated for or have a certification to be allowed to use in that type of environment, which would then involve potentially also the wiring and conduits and other things that you need to consider. So that's kind of a step one, safety first, so to speak. And then you need to look at the installation guidelines. There are some basic things. It's like clearly you don't want to put the sensor right in the path of the filling nozzle or filling so that the product is falling directly onto the sensor, which could then give wrong readings. Solids also have a dynamic about where you have a filling cone, where depending on your end there, and also you're going to have an emptying cone. So this is a dynamic that you need to keep an eye on. You may need to see, okay, where am I locating my level sensor to make sure that I get the measurements that I'm looking for here. Some applications of product, when we come back to that, certainly some of the more fine-grained or type of flours, sugars, and so on, might be sticky or hygroscopic, meaning that, if I get a little bit of moisture in it, they're going to stick to everything. They could also be very dusty. How does that affect the measurement? So things you need to look at there. Bridging and rat holing is another one. So if you do have a product that get a bit of bridging, and you have a level, and then you might have an empty hole behind it or below it, is there a way to address that? Usually not, because many or most level sensors out there will only see what the top level is of the surface here. So those are scenarios where you need to be aware of here. And then, aligned with the, sticky and dusty environment could risk of buildup and so on with the beginning there. And I'll go into most of these scenarios more in depth as we go through the presentation. So you get a better feel for what and how to address each one of these potential scenarios that you might run into. So if we start at point level switches, so generally for high level, low level alarm purposes, there is a wide range of different type of sensors. There's some that are more universal than others. I would say that some of the more universal ones that we see out there are the tuning fork. So like these ones here, but you have either one or two tuning forks that are oscillating, and they essentially detect the solids level as the product is covering these times. Then you have various based on capacitance type of sensors. Those are usually, like these ones here, smaller bins, where you have maybe a small hopper or something like that, where you just need to say low level or high level alarm. Many times those are very cost effective options to do that. And then if you get into really heavy duties, like some more really where you need rugged, maybe it's mounted on the bottom of a very tall silo, you need something really mechanically very strong, you may need to go to a capacitance type sensor there. So depending on where and how you're using it, you have choices and options based on the product, the size of the vessel, and also what kind of budget you're looking at. So like paddle switches are generally one of the more cost-effective ways of doing it. The trade-off with a paddle switch is that it's a mechanical paddle and it's going around. So potentially there's more that could go wrong with a mechanical motor turning a paddle than would you have with a capacitance or a tuning fork style where there's really no moving parts on it. All of these are in direct contact with a product, so you can mount them from the side or dropping in from the top, so you can have top level, high level alarms. There's also options for microwave barriers, so that's the ones we have on the lower right hand side here. There you have two sensors, actually a sensor and a detector on each side of a bin, and then a non-conductive window. So it needs to be a polycarbonate or some kind of plastic window, and it essentially looks through that window so that you don't have anything in direct contact with your product. So that's let's say a non-contact option for level measurement here. So those are the options that you have for solids point level switches. Then we get into the continuous level measurement. That's really when we start looking at the benefits getting through inventory or getting understanding what actually is on hand. And if we look at, let's say historically, that's still available. Historically, electromechanical systems were in place where essentially you had a weight on a measuring tape. So think about it like a guy somebody lowering down a weight, feeling it where the sensor is or the weight is touching the bomb, and then you look at your measuring tape and say, okay, this is 20 feet down. That's essentially what this does. It's just a mechanical way of doing that. It's a really fancy measuring tape, if you will. That still have its applications, still available and used out in the industry at times. Then we go to ultrasonic. Ultrasonic was for the longest time the primary method of using or for level measurement of solids. And it's still in use today. It's one of the more cost-effective options, especially for maybe shorter ranges, up to 20, 40, 50 feet or so. Ultrasonic is a very cost-effective way of getting level measurement in solids as well as in liquids. We'll focus most of the presentation today on free space radar and also followed a little bit by guided wave radar. Many of you might look as like, oh, free space radar, I remember back in the day it didn't work at all, and you will be right. There's been a lot of development just in the last 3 to 5 years using higher frequencies, different technologies, and a more sophisticated level of the digital signal processing of the signal using free space radar that today are allowing us to do things that just a few years ago we wouldn't even touch with a free space radar. So that's kind of where the industry is moving today, is free space radar. Great, certainly for the reason that you have no contact. There's nothing physically in the tank, nothing contacting the surface with the product itself there. So generally, if we can, we try to do free space radar as the first choice. If for some reason that is not possible, then we have the guided wave radar. Trade-off there is now you have a cable hanging down into the product. The benefit is that you generally get a absolute foolproof measurement that the guided wave radar provides you with there. So when we have maybe a little bit more difficult applications, guided wave radar may still be the better choice. There are not as many of those out there anymore, though. So if we look at, let's say, from Endres Hauser side, what we offer on the guided wave as well as free space radar, for liquids, there's a large full basket, everything from just basic level measurement all the way up to tank gauging applications with very, very high accuracy tank gauging measurements for liquids. But as we're looking at the solids here today, we have essentially 2 versions for guided wave radar, and then we have a couple of options here for free space radar. And today we will be focusing on the FMR67, which is this model here. And you can see this uses the 80 gigahertz frequency for the microwave itself. And I'll cover that in a few minutes here, why that is the first choice for solids applications. So we can have a technical background to that. So let's look at a couple of typical applications here then. So if we start with some of the harder ones to do. Some of the harder ones are really light powdery media. It can be fluidized. Sometimes you actually have fluidized beds to lighten it up to make sure that it's not compacting. So now you have a very light bulk density. And in these applications, depending on the height of the silo, the dielectric constant of the product, generally we would start looking at a free space radar. But if we realize, okay, that might come to, let's say, the boundary of reliability during all conditions, we might go and go over to a guided wave radar, like in this case here, the Level Flex FMP57. The guided wave radar, like I mentioned, generally have the highest reliability because it has the cable. It focuses that microwave energy very tight to that cable. And we also have a functionality we call end of probe function, which means that we always know where the signal is at. If you go and use microwave free space radar, even though it's slight, there is a risk that maybe under certain circumstances that you lose the the echo, and then the sensor may or may not know exactly where to pick it up again. Here with the guided wave radar, it always knows here's the bottom of the silo. So again, there are some trade-offs to using great guided wave radar. If you don't pay attention to it, maybe due to long-term use, abrasion and so on, could cause the cable to break. So that's potentially as a maintenance topic to keep an eye on that. And also if you have hygroscopic media, you need to use coated cables to make sure that you don't get crystals inside the cable that could then break it apart. So generally, like I mentioned, we start with guided free space radar, and then as we might move into guided radar if we're in need for it. For point level, generally it's a very simple choice, especially for light, fluffy media like fluidized bends, where you have a very low bulk density. The tuning forks are generally what we use there, but there's a couple of different versions that you can go to very, very low bulk densities. In dusty environments as well, this is where we may want to utilize some of the advanced diagnostics. I already mentioned the end of probe capability of a guided wave radar, but let's say if you're having a free space radar, in this case here, I know this picture may be a little bit hard to make out. This is actually an antenna from a free space radar, and as you can see, it's quite filled up with build-up into it here. And generally, free space radar will work just fine until you come to a point like, okay, there's just too much build-up on the antenna to really be able to get a good energy transfer between the antenna and the product and coming back again. And that's what some of these advanced diagnostics today allow us to do. It allows us to really look continuous at that build-up and say, okay, is this unit still working the way that it's supposed to do? And we can also run intermediate or unscheduled verification protocols to say, here's how it worked the day it was produced and installed. Is this device still running exactly the way that it did that day? So then we can say, okay, has anything changed? If everything is good, we're good to go. If we get some warnings or something like that, then maintenance can get involved and see what may need to be done. It might be a thing like cleaning the antenna, for example. Now, talking about cleaning antennas, clearly that's potentially a manual labor, and it's like you want to minimize or avoid that as possible, which is also why there is a possibility to do air purge. So if you have a traditional antenna, then you attach compressed air to it, and when and if the diagnostic tells you that you have build-up, then you do an air purge on it. So that works on this type of antennas. It also works on the antennas with a Teflon antenna, with a PTFE antenna. It's just a little bit different configuration, but the air purge is there to be able to blow off any dust or debris that might have accumulated on the antenna itself here. And we'll see here, I had this video, well, to see how well that works. So that's an example about how that could look like. If you have an antenna which is essentially filled up with a powdery buildup or other material, apply that air purge, you blow it all out, and now you're back measuring like you should again. If all the full energy is being transferred out. So here we now have a little bit different applications. So now we've gone from a really fine powdery product to the little bit larger grain sizes. So we talk about corn, beans, feed pellets, and so on that has larger particle sizes. You might still have some dust present, but generally these ones are a whole lot easier to measure in because they pose less of the challenges due to just the nature of the product itself here. And absolutely here is a free space radar first choice, hands down. It's kind of the go-to product for this one here. And then you might have a choice depending on the size and the height of the silo, vibronic or capacitance for the point level switches, where depending on you use it for high level alarm or low level alarm, and generally looking at the mechanical impact that you might have on a product sticking in from let's say in a tall silo. If and maybe there might be a need to have a protective roof above the point level sensor. If you have it sticking in from a side, you may need to have a protective roof on it just to protect it from product falling maybe 100 feet down towards it. Could have quite an impact. Just an extra protection for the sensor. So give you an idea about what we're talking about here now. So we're looking at this micropilot FMR67 in this type of silos. This one here is quite impressive. So this is a unit that was installed in the world's second tallest corn silo, which was close to 300 feet tall. And as you can see on the picture here, it's quite an impressive silo here. And this really would have been very difficult or pretty much impossible to do without the use of the 80 gigahertz and the 3-degree angle of the microwave energy focused down into this very tall, narrow silo. So that's where the developments have evolved over the last 3 to 5 years. Is that number one, started using the 80 gigahertz that then allowed us to go to this narrow beam angle as well. And to illustrate that, we have this picture on the right-hand side here. You have the radar unit, and you can see the very narrow beam going down towards the surface. Now, this is valid for liquids as well as solids, so this one is applicable to liquid applications as well. So especially if you have something where you have a narrow path and you need to shoot down in between here. So then you get this narrow path. So this then eliminates issues that you might have had in false echoes coming in from reinforcement on the sides, maybe build up on the side of the silo wall, or anything else that might have been an obstruction. It also allows you to mount it in a bit taller nozzle here. In the past, you pretty much had to have it flush or as close to the tank top as possible, so that the microwave energy, as it was coming back up at the microwave sensor, kind of found the sensor again. If it was sitting too high up, a lot of that energy was lost. But by using the higher frequency and narrow beam angle, now we also have a possibility to go up through a taller nozzle. For liquid handling, we even go through ball valves, so you can actually shoot straight down through a ball valve and still get a good reading in liquid applications. Right? So that then resulted in the possibility to measure in applications where in the past it was simply not possible. Something that the 80 gigahertz also allowed us to do is just from plain physics, looking at the wavelength itself. So if you think about the wavelength coming down from a microwave or an ultrasonic signal, you're going to have a certain wavelength. And depending on that wavelength, depending on the particle size or the grain size that you had here, you're either losing or getting a better reflection back from that surface. So if you had a very fine, smooth surface, think of it like a mirror effect. You send signal down here. If you have a very smooth surface, you're going to lose most of that energy out, i.e. like a mirror effect. Now, if you have any grains or something like that, you still get enough energy return back to the sensor. And if we look at the lower frequencies here, so the 6 gigahertz where microwave radar started out almost 25 years ago now, we need a really large particle, 50 millimeters. I mean, that's 2 inches, that's some really big pieces to get a good reflection back. Then some years ago, it evolved to 26 gigahertz, and we cut it down to roughly ½ inch or 11.5 millimeters in this case. So now we were progressing and we'd be able to use radar, free space radar, for finer and finer materials. And now ultimately with the 80 gigahertz, we're down to 4 millimeters. So that's about 1/4 inch, which generally you're going to have. Even if you have a sugar or some other fine surface, you're generally going to be able to get enough reflection because you're going to have a little bit of ripples on that surface there. So that's where we're combining, let's say, the capability of a narrow beam angle as well as the higher frequency is what makes possible to use free space radar reliably for a lot of solids applications where in the past it simply was not possible. So moving on to a couple of other applications, malt. We have a lot of breweries out there as well, and others that are dealing with barley or wheat and so on. It's also very light, low dielectric constant, and but again, here the free space radar works just fine, and then the same point level sensor, the tuning fork style point level sensor works excellent in malt and barley type of applications. One thing to consider as well is we don't always have narrow silos. So we looked at that 300-foot really narrow silo, then it's a matter of, let's say, aiming that sensor straight down the middle and getting as clean shot as possible down towards the bottom of that silo. But we also have a lot of large silos, large diameter silos, where we then need to figure out, okay, how do I get the best level measurement? But also I usually want to convert that into a volume, or potentially volume into a mass. Now mass, I'm cautioning about to do that conversion, because the product itself here, depending on how it settles and compresses, you may not always be able to say, okay, I have this level means this volume and this mass, because the mass might differ depending on how much the product settles in there. But volume you potentially can calculate out quite well. And then you're coming into the scenario here, okay, where do I position my level sensor? If I have a really large silo, and or I have a steep filling cone inside here, or an emptying cone, depending on, I want to measure both when I'm filling as well as emptying, you may need to have more than one sensor. So you may, like in a large diameter here, like in the picture on the left-hand side, you may need to have one closer to the wall so you can see where that level is at, and you have one in the center here, so you start getting an average, and then you take that into either a PLC or some other math module and say, okay, here is my average level inside this silo, and from that you can then derive what your volume is. For really large silos, like this one on the right-hand side here, you might need to go up to more. You might need to have 3 or 4. We've seen really, really large silos where we put 7 or 8 units inside of a silo. And then you're really getting a good measure of exactly what you have inside the units as well. Those are kind of the most reliable ways of doing it. There's been products on the market that have been using let's say a 3D type of method with mixed results. Sometimes they work well, sometimes they've kind of been a challenge to get set up and working properly. So there are possibilities out there. In my opinion, I feel that multiple sensors is the more reliable and easy way to set something up. And also, if there is an issue, you can look exactly where is this located and so on. The other part of getting the average value, let's say if you only have let's say like in the picture here on the left, instead of using 2 sensors, you may also be able to just use 1 unit and then use what we call a alignment device. And actually this alignment device is built into the flange on the unit itself here. And this essentially allows you to aim that level sensor. So if you mount it maybe a quarter of the way from the silo wall, and now you can still aim it down towards the center of the silo here. So then that generally gives you the best average as you have if you only want to put one sensor in there. So there are multiple ways of addressing the scenarios where you have large silos with multiple filling cones in the media. Not all solids are dry and powdery. We also have wet applications at times. So here's one example, spent grain. So this is essentially the leftover from a brewing process. where the malted barley has gone through the brewing process and it comes out, and this is usually sold to farmers and so on to use there. And as the silos or tanks, depending on the size, you also need to measure the level in there, because you need to know when you're about to fill up. This can be sticky, wet, steaming, and so on. And again, because of free space radar really doesn't care about, you know, if there's steam. We have this shape of the antenna, which is kind of like almost like a ball shape. So any moisture and condensation drips off very easily. So you don't have to be worried about condensation buildup on the antenna here. And you can see here we have two different styles, one with a flange and one with a threaded connection. So if you only have a threaded nozzle on the top, you'll be able to put it in there. And if you're a smaller brewer and you only have, let's say, a smaller bin, you may not need one of these units. You can also go essentially with an entry-level type of free space radar device, you know, good up to about 20 feet or so for level in these applications here. So there are, you know, an option for everybody, you know, from let's say more cost-effective way, just a basic measurement, all the way up to really high accuracy and more advanced functionality depending on what you're trying to measure. A lot of the food processing facilities are using blow molding, so essentially blowing their own bottles and or packaging. Generally that's PET or different types of plastic materials that arrive by truck or by rail car. And challenge with PET is generally it has a very low dielectric constant. And since microwave radar is relying on a change in the dielectric constant to get a reflection, you need to look at a couple of scenarios here. You know, what's the height of a silo, and what choice we have there. So generally, again, we start with free space radar, and if we get into really tall silos, we might go over to a guided wave radar, depending on, say, what other things are required in that particular application, looking at accuracy and so on there. So there are, again, solutions for this as well here. And you see, again, the tuning fork, generally the first choice for low-level and high-level alarms. We talked a lot about level measurement, but clearly in solids handling, we're only looking at the level. We're also moving this product. Okay, it could be conveyor, pneumatically conveyed, screw conveyors, belt conveyors, and other ways, just dropping it down through a chute might be a possibility to do it. And when you're moving product, especially solids, you need to pay attention, make sure that it doesn't get clogged up or stuck for some reason. Because generally there's a lot of manual labor and a lot of work to go in and clean that out or free things up. So by using this little microwave Doppler sensor, so essentially you can mount it in a chute levis here, you can mount it externally coming off of a belt, or looking through a window into a silo or something like where you're moving product. So you essentially get a indication of, is this product still moving or is it getting plugged up, particularly in pneumatically conveyed lines. You want to know right away if things are starting to slow down in there. So it's a simple way to do just that. Clumping and other things often is a result of moisture. So that's another area to potentially look at. You know, what is the moisture content in my product? Am I aiming? Am I drying something? So I'm looking to achieve a certain level of moisture or removal of moisture in the product, or is it a product where I want it a little bit wet? So I want to know what is going on in the process. So there is also a number of different ways to actually continuously measure the moisture content in solids. Here we're talking about grain handling and grain drying and handling, but it could be more or less any solids as well. So there is a handheld version. Here's one that we put inside silos. So two little sensors go in there. Here's one. This graphics maybe could be a little bit better. This actually indicates where you could put it inside of a chute where the product is falling onto the sensor, and as it's falling on the sensor is detecting what the moisture content is here. So mainly during loading or offloading or transferring from one location to another one, would we use this type of sensors here, like this MMP42, for example. So those are additional measurements that you can do or may be necessary to do in solids handling if you're for some reason needing to measure the moisture on a continuous basis. So now I talked a lot about the technologies behind the actual measurement itself. So now you have that, you're getting reliable information from each one of the silos. Now, how do you connect? How do you tie it all together? And who needs this information, and what are we going to do with it? So there's been a lot of different ways of bringing this data back together again, so that the people that need it for production, for procurement or inventory control for whatever reason, for reordering and so on, have a clear picture. They get their piece of information. It could also be information going to maintenance. So you communicate out the diagnostics and say, okay, silo number 5 on location number B seem to have a problem. You need to send somebody from maintenance to have a look at that one. So getting the right information to the right person at the right time. Several ways of doing that, connecting the sensors either wired or wirelessly to let's say collection unit, and then bringing that into a central software. And from Endres Hauser, we offer the supply care software package or solution, which is scalable, so you can start small and add on to that. And from this here, you can then do all your scheduling, planning, keep an eye on it, and being also a cloud-based solution, you can have it either on an enterprise level or on a cloud-based level. So depending on who needs it and what your philosophy from a let's say data security side of things, there are different options. And what I just mentioned here is like, let's say a sensor is going bad out on the tank, comes in information, somebody from supply chain looks at it, say, okay, we need to reorder this product, or maybe your supplier have that information, so they see immediately, oh, you're running low here, I'll just send a truck right now, so that we kind of bypass one step. That's one part of it. But you might also have somebody in maintenance using just a handheld device, getting text or email messaging, keeping them continuously updated about what the health of the entire system is all about. So to sum it up, in conclusion here, the foundation for inventory management is the reliability of the actual measurement itself. And I hope I help you get a picture of, let's say, what the options are, what your options are. Generally start with the 80 gigahertz free space radar, and if for some reason that may have restrictions to it, then you have guided wave radar, ultrasonic, or electromechanical, as other options as well. And the switches, not only there for the safety, but also for production efficiency. Did you fill that silo up to the top level, or is there maybe additional space in there? Are we at the low level right now? We're about to run out, so there's a lot of aspects to that. And then when we get into the inventory monitoring, real-time information about what you have on hand anytime during the day from wherever you happen to be. Many of you, just like me, are working from home. How do you keep track on this if you're not physically on a location somewhere? So that gives that complete seamless visibility to all the stakeholders in there. Okay, with that, I'm gonna wrap up, and we're gonna go back to Jürgen and see if we have some questions.
Yeah, thank you very much, Ola. I try to answer as many questions as possible, and so far it looks good. We have some more, but before I come to the questions, I just want to tell the participants that all the devices that you have seen are linked in the handout, so you can just click on the link symbol, and then you will be directed to our webpage, where you then can directly find this. Yes, Ola shows it again. So just click on in the handout, and then you will be directly guided on our webpage to the devices. Also, what I would like to tell you, and perhaps you can go back to the last slide, In case that you would like to follow us in the future for our webinars, we can or we will offer more webinars, especially for the food industry, but in general we are offering webinars. You can find them on our webpage on endres.com, so just go to events. We have an event section there, and then under seminars, roadshows and webinars you will get the complete overview of webinars that we are offering. Specifically for the global food webinars, we are planning to have new ones from July on. So this was a series of 4 webinars that we had within the last 4 weeks. And we go on with this in July. Ola, we have some more questions. Perhaps we cannot probably go through all, but again, we will answer them after the webinar. Perhaps one is here, does the grain size matter? Does the grain size matter if you measure? And is the flow rate important for such devices?
I'm not sure if I entirely understand your question. So what I mentioned earlier here, I'll just go back to that slide to indicate that. So the particle size might matter, yes, depending if you have very fine-grained media, like a powdered sugar or some other media, then that you need to be a little bit extra careful. If you have anything with any grain sizes or any particle size, generally no worries on that at all. So that is maybe answering that question there. Not sure if I understand the question really related to flow rate, because when we're looking at solids and level, we're generally looking at what the static level is inside the silo.
Yeah.
Maybe if I make a guess there, is that when you are filling the product into the silo, I hope I'm addressing the question correctly, that as the level is changing, generally the level is changing, well, it's always going to be changing slow enough for the level measurement to keep up with that. So there will be no concern about the level keeping up with the rate of filling inside of the silo. Again, you want to make sure that if you have your level sensor here, you fill over on this other side. You don't want to fill directly into the path. So on the graphic we have on this picture here, if you have your filling coming in from this side and your filling line is interrupting the free space radar path, then you potentially would be picking up the filling stream instead of the actual level. So you want to make sure you mount your sensor in such a way that it's not being interrupted by the filling stream.
Okay, perhaps we can go through one more question as well. What about if you have more than one radar device in one application? So if you have multiple sensors, will the different signals cause issues for the devices?
No, they do not interfere with each other. No, not at all.
Right. Good. And then perhaps the last question that we take, and again, we will of course follow up on all other questions. Can such a device that we align also be used for liquids, not only for solids?
I guess you could. I'm not sure. Well, I mean, the liquid is always going to be a horizontal surface. I guess maybe the question is, what if I have a domed roof, and if for some reason, if you're not able to go back here again, if you're not able to have a flange which is level like this, I guess you could mount it like that and then aim it. But in my experience, most flanges are mounted horizontal to the liquid level. So could you use it? Yes. I struggle to see when and where that would be necessary.
Yeah. Good. So now I see we get more questions in. Again, we will follow up on them, but unfortunately we are already out of time. I think with this, thank you very much, Ola, for this really great presentation. Thank you very much for your participation. We hope to see you again in the future. Again, follow us on endres.com. Follow us also on our channels, for example, on LinkedIn, where we also give the notifications out when we do new webinars. And in case that you would like to watch the webinar recordings, you can also find them on our webpage. With this, I wish you a good day, a good evening, wherever you are in the world, and hope to see you soon again. Bye-bye.
All right. Thank you, everybody.